minus 1. The method we have learnt in earlier topic will be applied here. X coordinate of center of mass of the three particle system will be m1 x1 plus m2 x2 plus m3 x3, m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3. Here m1 is 1 kg and x1 is 2, m2 is 2 kg and x2 is 2, m3 is 3 kg and x3 is 1. 1 plus 2 plus 3, that is 2 plus 4 plus 3 by 6, 9 by 6, 3 by 2. Now y coordinate of center of mass will be m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. Here m1 is 1 kg and y1 is 3, m2 is 2 kg and y2 is minus 1, m3 is 3 kg and y3 is minus 2. Minus 2 minus 6 by 6 minus 5 by 6. Hence the coordinate of center of mass can be derived with the method which we have discussed here. Now we will discuss vector method of finding center of mass. Center of mass of two particle system. Let two particles of masses m1 and m2 are at point P and Q. The position vectors of point P and Q are r1 and r2. Center of mass of this two particle system lies on the straight line PQ, and the position vector of center of mass is r. Let two particles of masses m1 and m2 are at points P and Q whose position vectors are r1 and r2. Now the position vector of center of mass is now the position vector of center of mass is r equals to m1 r1 plus m2 r2 by m1 plus M2. This concept can be extended for a multi-particle system. Center of mass of 2 points lies on the straight line joining the points. Center of mass of a 2-particle system always lies on the straight line joining the particles. Now we will discuss physical significance of center of mass. Center of mass is the point where the total external force can be supposed to act. Center of mass is the point at which the total external force can be supposed to act. If external forces acts on a system, then center of mass will be in motion, and in absence of external forces, center of mass will be at rest. If external forces acts on the system, then center of mass will be displaced in absence of external forces. Center of mass will be at rest. One important discussion we must learn here: in absence of external forces, center of mass will be at rest, but different components of the system may be in relative motion due to internal forces. That is, motion of motion of different constituents of the system due to internal forces does not affect the position of center of mass. Center of mass will be displaced only when external forces acts on the system. It is not necessary that there must be a material particle at the point of center of mass. Center of mass of a rigid sphere also lies at its center, and center of mass of a hollow sphere also lies at the center. It is not necessary that there must be a material particle. There must be a material particle at center of mass. For example, center of mass of a solid sphere lies at its center and center of mass of a hollow sphere also lies at its center. Now we will discuss methods how to find this central mass of continuous bodies. Center of mass of continuous bodies. We have to apply concept of calculus, particularly integral calculus. We have to apply concepts of calculus. Coordinates of center of mass of continuous bodies is given as coordinates of center of mass of continuous bodies is given as and z coordinate of center of mass of continuous body equals to 1 by m, where a capital M is total mass of the continuous body. I will take an example so that we can learn how to find central mass of continuous body. Center of mass of a uniform rod. Let length of a rod be L and mass be M. Let mass of rod equals to M and length equals to L. Then mass per unit length equals to N by L. We take one of the ends of the rod as origin. Let a very thin element of width dx and mass dm is at a distance x from one of the ends of the rod. Let us consider a very thin element of width dx and mass dm at a distance x from one of the ends of the rod. As mass per unit length equals to m by l, Hence, mass of this element of width dx will be now dm equals to m by l, that is mass per unit length, into width of element dx. Hence, dm equals to m by l into dx. Now, coordinate of center of mass of the rod is given as coordinate of center of mass of rod is given as x equals to as the length of rod is L, hence lower limit of the different integral will be 0 and upper limit will be L. X into dm and dm, we will place the value of dm m by l into dx. Here both m and l are constant, hence we can take m by l out of the integral sign. This and that cancel. Integration of x is x square by 2 First we put the upper limit of the definite integral and the lower limit, that is 1 by L into L square by 2. Hence, coordinate of center of mass is L by 2, that is center of mass of uniform rod will be at its center. Hence, center of mass of a uniform rod will be at its center. Now I will discuss center of mass of some continuous bodies. Position of center of mass. First, uniform rod. Position of center of mass. Center of rod. Ring. Center of ring. Disc. Center of disc. Solid sphere. Center of sphere. Hollow sphere. Center of hollow sphere. Square or rectangular lamina. Point of intersection of diagonals. Intersection of diagonals. cone at a height h by 4 from base of the cone on the straight line joining center of base to the vertex. I will discuss the application of center of mass in part 2 of this video. Thank you.